Okay, so this is a video where I will be walking through this final that was shared with us from the past. So I'm going to be walking through how to do each of these questions. I might make the occasional mistake, so be on the lookout for that. Don't take everything at face value. So this is an 8-question long final. I did add a couple of extra questions just in case we're going to have maybe some conic sections or exponential growth on there, right? Just give us a little bit of extra practice so that we can kind of cover our bases. But we are going to start with number 1 up here. So for number 1, for all 3 of these, we want to determine whether this limit exists, is infinite, or does not exist, right? So for this first one here, that is the limit as x approaches 1 of the absolute value of 1 minus x squared over x minus 1. Now, what we see here is, of course, that absolute value kind of messes things up. And even if we plug in that 1, if we try to plug and chug, we're going to get an indeterminate form of 0 over 0. So what we have to do instead is, take a look at around that spot. So in order to determine if this limit exists, we'll want to look at the limit from the left and from the right. Now there might be better ways to do this, but I personally feel like the easiest way to go about this is to just do a brief little XY values chart to figure out about what each of these limits should look like. So approaching from the right side means that if I had something like this and this is 1, approaching from the right means I'm approaching from all of these values. So I'm going to be approaching this way, getting closer and closer to it. So all of my values should be larger than 1. Obviously this isn't this graph, that's just an example to help us visually understand what we're doing there. But so let's come up with some x and y values for approaching 1 from the right. We want to get really, really close. So I'm going to get some really close x values. I'm going to say maybe 1 1/4, 1 1/2, and then maybe 2, 3, and 4. We're just going to plug in those values and just kind of see what we get, see how what value we're approaching. So let's start over here because we'll start big and approach that x equals 1, right? So plug in that 4, that's going to be the absolute value of 1 minus 4 squared over 4 minus 1, so that's 15 over 3, which is 5. Plugging in that 3, that's going to be 1 minus 3 squared, which is 1 minus 9, or 8, over 3 minus 1, which is 2, so that is 4. Plugging in the 2, that's going to be 1 minus 4 over 1, which is 3. Okay. And so we're going at a pretty constant rate here. But as we get closer to 1, let's see what happens if I plug in that 1 1/2. I know 1 1/2 is the same as maybe 3 halves. 3 halves squared is 9 halves. 1 minus 9 halves is going to be, 1 minus 9 halves is going to be negative 7 halves, but in that absolute value comes out to 7 over 2. And then we've got 1 1/2 minus 1, so that's over 1/2, right, which is the same as this because we multiply by the reciprocal, which is, oops, I feel like I messed up something there. Let me just, 1 1/2 is 3 halves. There we go. That squared is not 9 halves, it is 9 fourths. I told you I might make some mistakes of my own. 1 minus 9 fourths is going to be negative 5 fourths. In that absolute value, we just get 5 fourths. And then that is over 1/2 because it's 1 1/2 minus 1. which turns into 10 fourths, or 5 halves, or 2.5. Okay, 2.5. It gets a little trickier when we get those fractions going, but it is necessary to get us closer and closer, get a good idea. Let's try that 1 1/4. I know 1 1/4 is the same thing as 5 quarters. This squared is going to be 25/16. 1 minus 25/16 is, I believe, negative 9/16, right? Because 25 minus 16 should be 9. Yep. Okay, so we're going to get 9/16, and that's going to be over 1/4. So it's going to be 36/16. Or I could reduce that to, of course, 18/8, or 9/4, which is 2 1/4. And we see as we get closer and closer to an x value of 1, which at 1 it's undefined, but as we get closer and closer to an x value of 1, we're getting closer and closer to positive 2. So our limit approach as x approaches 1 from the right side of this is going to be 2. And now we're just going to do that same thing, but approaching from the left. So now, do a different one. So we're going to approach from the left. So we'll say that that closest x value is going to be 1/4 less than 1. So it's going to be 3/4. And then maybe we'll do 1/2, 0, -1, -2. We'll try plugging all those in. Again, let's start from this furthest part and work our way closer to that, so that we're actually approaching that value kind of with our work. Plug in that -2, that's going to be 1. Well, -2 squared is 4, so 1 minus 4 is -3, but an absolute value. And this time it's -2 minus 1, which is -3, so this is a -1. Plugging in that -1, I'm going to get 1 minus 1, which is 0, over, and this is okay because it's a -1 minus 1, which is -2, so that's just 0. And it looks at that like that might be the center of this absolute value function there. Plugging in that 0, I'm going to get a 1 up top, and 0 minus 1 is -1, so this is -1 again. Plugging in that 1/2, it's going to be 1 minus 1/2 squared. 1/2 squared is going to be 1/4. 1 minus 1/4 is 3/4. 1/2 minus 1 is -1/2. This becomes a -6/4, or -2.5. And now I plug in that 3/4. 3/4 squared is going to be 9/16. 1 minus 9/16 is going to be 7/16, I believe. So 7/16 over 3/4 minus 1 is going to be 1/4. So this is going to be 28/16, or I could write it as 7/4, which is 1. No, it's not. I feel like I made a mistake. I'm going to back up and redo that just to be sure. So we're plugging in 3/4. 3/4 squared is 9/16. That's correct. 1 minus 9/16, so it's going to be 16 minus 9 is 7. Okay, so this is going to be 7/16. 3/4 minus 1 is -1/4, which is -28/16. And I'll just reduce that the long way rather than trying to do that in my head. Okay. Interesting. I still feel like I made a mistake, but that's going to be -1 and 3/4. I'm going to double check this because I checked all my answers to make sure that I knew how to do these before I started recording this. So I know that this limit should be -2. But this ends up contradicting that. So I want to, let's double check plugging that 1/2. So it's going to be 3/4 over 1/2, which is 6/4. Oh, yep, that's where I messed up. That is not a -2.5. It's a -1.5. I don't know why I thought that was 2. Sorry about that. Okay. But we see that this is approaching from this way, and it's getting closer and closer to a -2. So since these limits, although they're both approaching a 2 of sorts, since this one's positive and this one's negative, this limit diverges and therefore does not exist. And that's exactly how you would show that on the exam, is you would figure out these limits, and then you would probably want to write that since the limit approaching from the right does not equal the limit approaching from the left, the limit does not exist. Right? Because that is our pretty big prerequisite for a limit existing, is that the limit from the left and from the right are equal. Next step is 1b, and this is the limit as x approaches 1 from the right side of x squared over x minus 1. Now for this one, we of course don't want to just try plugging and checking, because we'll get that 1 in the denominator. But it doesn't matter if we plug that in and get something that doesn't work, because this is approaching from the right side. So again, we're going to want to try some values and take a look at what that's like. So let's see here. So approaching 1 from the right side, I know 1 is undefined. Let's go bigger. Let's go 1 1/4, 1 1/2, 2, and 3. Okay, and I actually am going to erase that. I'm just going to put an X above it, or in red, so that we know that that doesn't exist, because that takes up a little less space. So let's plug in that 3. So I get 3 squared is 9 over 3 minus 1, which is 2, which that's going to be 4 1/2. If I plug in that 2, that's going to be 4 over 2 minus 1, which is 1, which is 4. Plug in 1 1/2. 1 1/2 squared. Remember, 1 1/2 is the same thing as 3 halves. That squared is 9/4 over 1/2. It's going to be 18/4, which is 4 1/2 again. Interesting. And then if we plug in that 1 1/4, that's going to be 5/4. Square that. 25/16 over 1/4. That's going to be 25/4, which is then 6 1/4. And while that may not be immediately clear as to what that limit is, I want us to look at how much it's changing. Like what, I guess the slope would be the right word there. So I'm going 4, 4 1/2, that's a really small change. But then even though I went a very short distance away on my x plane, I jumped up pretty high, a higher difference than I was jumping up this way, which tells me that as we approach x equals 1, right, starting over from this 3, that tells me that we've got, say, 4 1/2, 4, 4 1/2. Oops, should write that out a little better. So we've got and it's going to look something like that, which tells me that it is approaching infinity, because I know that's just going to get higher and higher that way. So this is approaching infinity. I hope that made sense. Identifying when it approaches infinity, algebraically, like that has always been a tough point for me. This next one is a tough one. So it's the limit as x approaches infinity of the square root of 4x squared plus 3 over x. Now this is difficult at a glance, but we'll see that for a lot of questions like this, one of the first steps that we take is to divide by the highest order power. So I'm going to divide all of this by x squared. And so I'm going to, okay, so I don't have a good way to explain that. But inside my radical, I'm going to take this and divide it by x squared. So we're at 4x squared divided by x squared plus 3 divided by x squared. But obviously it's a different thing now. So we'll multiply that by x squared out in front. And that may seem counterintuitive, right? But to be clear, having this x squared out in front undoes the division of these x squareds, right? So if I were to then multiply that out, this would all cancel and it would return back to this point. The reason that I've separated, because this is equal to this perfectly still, but the reason I've done it this way is because I want to kind of separate it out. I want to manipulate this equation. And what happens is because this is multiplied with all of this, I can actually pull this out of the radical. So that's going to be So obviously the square root of x squared is x. So now I've got this, and of course 4x squared divided by x squared is just 4, and then 3 over x squared, and that's all over x. And now since I've pulled this out, I can cancel those x's. Which again, it might not be clear immediately why I'm doing this, but I really hope that it'll make sense once this gets finished up. So now, instead of having this, where it's difficult to tell what's happening, we've reduced this equation to just this. So now it is the limit of just this square root here. What we can do now is essentially ignore that square root, and I can do this, which I personally find kind of fascinating. So this is the limit of this first term plus the limit approaching as x approaches infinity of this here. Of course, the limit of a constant is just that constant. So that's going to be 4 plus this limit here. Well, I know if this gets exponentially bigger and bigger, then this is going to be approaching 0 since that's a constant. So this limit is going to be 0. So it just equals the square root of 4, which is just 2. And I made a mistake because this is really hard to read. This is approaching negative infinity. Which I believe means that this is approaching negative 2. I don't have the energy to go back and figure out how that changes it actually. But if that was just positive infinity, it doesn't change much. I think it just changes the sign of the answer in this case. But I hope that that made sense. I'm just going to pretend that that's positive infinity. So it equals 2. Sorry. Let's take a look at this number 2 now. So we've got f of x equals x to the 5th plus 5x to the 3rd plus 2. And we want to prove, or we want to show that it has a 0 somewhere in this interval. Well, if we remember, we can do this using the intermediate value theorem. Or just IVT, which is probably how I'll refer to it during this. So there's, of course, two constraints for the intermediate value theorem to work. We have to have, on an interval, our function has to be continuous. And then also on the interval, it has to be negative at some point and positive at another point in order for us to be able to claim that there is a 0 on that interval. First of all, we can tell that this is continuous because there's nothing here that would make this function undefined at any point. There's no discontinuities present. There's no absolute value. It's not a piecewise function. So there's no holes. There's no jumps. There's it's not a fraction at all, so there's nothing down here. So this is continuous always, which means it's definitely continuous on this interval, which you'll want to say that on the exam. If they want us to show that that has a 0, we'll want to say that this function, so f of x, is continuous on the given interval. That we know, okay? Big important. The next step is to figure out if it is negative at any point, and then if it is positive at any point. So if it's greater than or less than 0. So I'm just going to plug in these endpoints since this interval is inclusive. So let's see what f of -1 is. That's going to be -1 minus 5 plus 2, which is just -4. So that's less than 0. Okay, let's try plugging in the other endpoint. That's going to be 0 plus 0 plus 2, which is greater than 0. So because at this point it's less than 0, and at this point it's greater than 0, and it's continuous on that function, in order for it to go from negative to positive, but from here to here, since it's continuous, it must cross the x-axis, meaning there must exist a 0. So because of this, you would say that there must exist, or there must be some value c such that f of c equals 0. So there must be some x value on this interval where when we plug it into the function, it is a 0, when it crosses that x-axis. That's all that that means. And that's how we show that with our intermediate value theorem. If we're confused as to how that intermediate value theorem works, again, remember that I do have a video on that you can go review. It should be in this same playlist, but I will just go over it really quickly. If I have a function like this, where it is continuous on maybe this interval, on maybe this interval, down here it's negative, and up here it's positive. Because it's continuous, I know that it must cross this x-axis somewhere. And by crossing the x-axis, that is a root, that is a 0, that is an x-intercept, those are all synonyms. So it has to cross the x-axis, which means there has to be a 0, where this 0 might be at some value where x equals c, where we don't know what that value is exactly. And I believe actually for that function in particular, that it has a 0 at 0, no. I know that the 0 is a long decimal in there somewhere because of when I was checking it. But let's move on to the next one. It says assume that a function x has the property 1 minus e to the x squared is less than or equal to f of x, which is less than or equal to x to the 4th. And we want to calculate the limit as x approaches 0 of f of x. That might look intimidating at first, but if we take a look at how this is presented to us and we want to calculate the limit, the one thing that I know of that has this like less than or equal than, greater than or equal than nonsense, it puts it between two things, it sandwiches them between, that has to do with limits, is our squeeze theorem, or the sandwich theorem, however you know it. Which means, and we will check now, let me take the limit of this. So if this is true, then of course the limit as x approaches 0 of this first thing is going to be less than or equal to the limit as x approaches 0 of f of x, which is going to be less than or equal to the limit as x approaches 0 of x to the 4th. And that's just true because of how these functions work. That's like, if I have, here I'll color code this, so I have this function, and I have this function, and this function. Of course, no matter what limit I'm looking at on here, since this function's greater than this one, this limit is going to be greater than or equal to this one. And the same down there. So that's essentially what we're looking at here. So based on this, we can conclude this. Now, using that squeeze theorem, if these two limits are the same, that means that this limit must be the same as those two. So let's figure out this limit. This one, we can actually just plug it in. We'll just use that substitution. So plug in a 0 for that, and that's going to be 1 minus e to the power of 0 squared, which is 1 minus e to the power of 0, which is 1 minus 1, which is 0. Okay? So this limit is greater than or equal to 0, and then less than or equal to whatever this limit is. Well, once again, we can use substitution and just plug that in. This limit is also 0. Since these limits are the same, that means that this limit must equal 0, because it is greater than or equal to 0, and it is less than or equal to 0. Therefore, this limit equals 0. And again, you would want to, they say to clearly indicate any theorems you were using. So I would literally write out the word squeeze theorem or sandwich theorem on your exam if you have a question like that. Just to be 100% certain that you're meeting those requirements. This next one, we just want to find the first derivative of this function f of x, where f of x equals this. And luckily for us, we do not need to simplify our answers. So we can just use that quotient rule and just leave it alone. So quotient rule, I remember, is going to be that low d high minus high d low over low low. So it's going to be this bottom term. It's going to be e to the x plus x squared times the derivative of the high term, which is 2x, minus the high term, which is x squared, times the derivative of this bottom term, which we do need to use chain rule there. So I'm going to say my outside is something squared, and my inside is e to the x plus x. Where this, of course, we can use that sum rule. So the derivative of e to the x is just e to the x. The derivative of x is 1. So the derivative of this top is going to be the derivative of the inside times that power times the inside, right? Because this is applying that power rule and then just chain rule multiplied by the inside. So the derivative of this part is just going to be 2 times e to the x plus 1 times that original inside, e to the x plus x. So that's a lot, but we can just write it like that. We don't have to simplify. And so that finishes off this. So now it is all over low low, which is just e to the x plus x squared squared, which is going to be to the 4th. And that's it. That's all you have to do for that one, because we don't have to simplify, thank God. It's still good habit too, so if you'd like to practice simplifying that, I recommend it. You can always double check it with like an online calculator or something. But I'm just going to leave it like that for now. This should be correct. I checked all my answers before, so I'm just hoping that I don't mess them up while recording. This next question, we want to find the second derivative of this function h of x. Like so. And so this is obviously going to use some chain rule. So we're first going to take that first derivative. So we're going to take the derivative of the inside times the derivative of the outside, which is going to be negative sign. So I'm going to put that negative in front. Then this is same thing. So the derivative of the inside, which is negative sine of x, times the derivative of the outside, which the derivative of e to x is just e to the x. So boom, there's our first derivative. Now our second derivative, we're going to do the same thing, except now we also have to use that product rule. Yeah, because I have these products of things that are all differentiable. So remember, our product rule is the first term times the derivative of the second plus the derivative of the first term times the second. So that's going to be negative e to the x times, well, this is chain rule now, so the derivative of sine of e to the x is going to be the inside times the derivative of the outside. So I'm going to have e to the x times e to the x, so it's going to be e to the 2x times cosine of e to the x. And that's just this first part, so now I have to do the second part, so that's going to be the derivative of negative e to the x, so which is just negative e to the x, then times that for that second term. Now we have to do that same product rule with this term over here. So of course it's going to be that first thing times the derivative of the second. I know that the derivative of e to the cosine of x is going to be negative sine of x e to the cosine of x. So I'm going to take this, multiply it by this, which turns that positive, lucky us. That's going to be sine squared times e to the cosine of x. And now plus, it's going to be the derivative of negative sine of x times this, which is going to be negative cosine of x. And there we go. That one's a lot, and it's kind of a lot to keep track of. But this is it. And once again, we don't need to simplify, so we can just leave it like that, which is wonderful. Okay, this next one's a tricky one because it's working with volume a little bit. So it says we want to construct a cardboard box with a rectangular base whose length is twice its width. The volume of this box should be 72 cubic centimeters, and the box should have a top. We wish to minimize the amount of cardboard used in the construction. And they basically just tell us the requirements, like we need to draw it out, we need to label everything clearly, blah, blah, blah. So for this, I'm going to draw out, I'm going to sketch out a little rectangular prism, little cardboard box, and I'm going to say this is my width, this is my height, this is my length, and we know the length is twice the width, so I'm going to do that. We know that our volume equals 72 cubic centimeters. And since we want to minimize the amount of cardboard used, we need to know how much cardboard we can take, which is going to be surface area. So surface area, if you'll remember, of a rectangular prism, which if you don't just memorize it, it's pretty easy to figure out because it's just the area of one side plus the area of another plus the area of another, and then all that times 2 because we've got double of each sides. So it's going to be 2 times length times height plus length times width plus width times height. Okay, and I'm going to move that over. So V equals 72 cubic centimeters, just so we don't forget. Now from here, well, actually, before I plug anything up here, we want to put everything into a single variable. And since the length is 2 times the width, I've got 2w and w, I'm going to try to turn everything in terms of w, which means we need to figure out what our height is in relation to the width. That's not something we can really do with this equation right here, but I know that volume is length times width times height. I know the width is the width, and the length is double that, so it's going to be 2w times w, which is 2w squared times h, and that all equals 72. So if I want to isolate h, so now h equals this, and I am going to simplify that, so that's going to be 36 over w squared. Now that we know our h in terms of w, and everything is in terms of w, we're going to plug that back in up here. So it's going to be 2 times 36 over w squared times 2w. So it's going to be 72 w over w squared. One of those w's cancels. So it's going to be 72w, or 72 over w, sorry. Plus now our length times our width, which is going to be 2w squared. Plus our width times our height, which is w times 36 over w squared. So that's just going to be 36 over w. Then from here we can distribute, well, can actually combine some of these terms, right? 'Cause we can combine those two. But I am also going to distribute this, so I know 72 plus 36 is 108. 108 times 2 is 216, so it's going to be 216 over w plus 2w squared. Okay, so we know that our surface area, I'm just going to rewrite it up here, can be represented like so. If we want to find the, we want to find the width that would minimize our surface area. So we want to find a minimum. We know how to find a minimum, right? We're first going to find our derivative of this. And then set that equal to 0 to find our critical points. So the derivative is going to be 4w. Then this is going to be minus 16 over w squared. And let's just work with the power rule. So now I'm going to set this equal to 0 to find those critical points. It's going to equal 0 at something. We need to manipulate this so that it equals 0. I'm going to add this to both sides. So it looks something like this. And now I'm going to multiply both sides by that. So it's going to be 4w cubed. Oh, I made a mistake. Backing up. This should not be 2w squared. It's 2w squared times 2. That should be a 4. Which means this should be 8. That's 8. That's 8. Sorry. Okay, so it's 8w cubed equals 216. If I divide this by 8, that's going to be 27. And I know the cube root of 27 is 3. So w equals 3. So now we need to figure out if that is a minimum, because we do need to prove that, right? We have to draw our rough sketch and label our variables. We did that. We have to write our constraints to write a function in a single variable. We did that. We need to find the critical value of the vector function. We did that. Now we need to show that we have a relative minimum at the critical value, which means we want to take a look at the interval. I'm just going to write it like this because that's easiest. So now we're going to do what we always do. I want to see if it is increasing or decreasing in these intervals using my first derivative test. So I'm going to take this. Let's try plugging in a 1, right? Because that's on this interval. Plugging in a 1, I'm going to get 8 minus 216 over 1 squared. So it's 8 minus 216, which is definitely negative. So this is decreasing. So it's going to look something like that. And then from here, let's just plug in a 4. So it's going to be 32 minus 216 over 4 squared. So 216 over 16, which, let me figure out that just to make sure we're doing that right. So that's going to be 108 over 8, 54 over 4, 27 over 2, which is definitely less than 32. So this is positive, and therefore increasing, which is going to look like that, which tells me that at x equals 3, or sorry, at w equals 3, we have a minimum, so that should minimize our surface area, which we did that. I'm frankly not sure what they want here because that feels like the same question there. They might want just an explanation of this like verbally. But yeah, so I'm just gonna move on past that for now. Let's take a look at number 5 now. Good Lord, this video is gonna be so long. I hope it's helpful. It should be chock full of info. But so f of x, we're told that f of x equals 4x squared over x squared minus 4, and that the derivative is negative 32x over x squared minus 4 squared, and that our second derivative equals this. Oops. Okay. Wow, that got crooked fast. Sorry. So we first want to find the domain. So we're going to look at our function, and we're going to see if there's anywhere where it is undefined, or just discontinuous, right? I see obviously our numerator has nothing like that. It has no radicals, no nothing. But our denominator can equal 0, and obviously we can't have that. So let's set this equal to 0, x squared equals 4. So it is discontinuous when x equals positive or negative 2. So x cannot equal 2, and it cannot equal negative 2, which tells me that a domain should be literally anything other than that. So I'll write it in the form we like, which is this. Remember, those round parentheses mean it is not included in that. Okay. Next, we want to find all horizontal and vertical asymptotes, if there are any. Now, it's generally good rule of thumb that if you have a discontinuity from something like this in the denominator, it's probably an asymptote, but it could be a hole. So you always want to check if it's a hole, and it would be a hole if you can factor out that discontinuity from the numerator at all. We can't do that here, so it's safe to say that there are vertical asymptotes at both of these points. So our vertical asymptotes are at x equals 2 and negative 2. And then we want to check for horizontal asymptotes. If you'll remember, that's based entirely on the highest power of the numerator and denominator. In this case, since these powers are the same, our horizontal asymptote is the top divided by the bottom, so that's 4 divided by 1, which is y equals 4 is our horizontal asymptote. Next, we want to do pretty much all the big stuff. So find our intervals of increase and decrease, relative maximum minimums, where it is concave upward, and inflection points. So let's see if we've got any critical points. Of course, we've got these discontinuities, but also we've got a critical point at x equals 0, which is helpful. Just kind of bubble all those in. And let's check for inflection points. Of course, we've got those discontinuities, but that doesn't count. So I know that my numerator will equal 0 whenever all this equals 0, which, if I work with that, I'm going to get x squared equals negative 4/3, which would mean if I take that square root, I'm going to be taking the square root of a negative number. So this doesn't exist. That would be imaginary, which means that there are no inflection points. So there are none. So now it's just a matter of setting up our intervals. So it's going to be from negative infinity to negative 2, from negative 2 up to 0, because that's a critical point, 0 up to 2, 2 up to infinity. And now we just need to check our intervals for increase and decrease. If I plug in, let's say negative 3 into my first derivative, I'm going to get negative 32 times negative 3, which is positive, over anything in this denominator is going to end up being positive because it's squared, which means that this is increasing. If I plug in, let's say negative 1, it's going to be the same thing. Negative, negative is positive, positive in the bottom, still increasing. Now I'm going to plug in a positive 1, and that's going to be negative 32 times 1, which is still negative. So this is decreasing. If I plug in a positive 3, we're going to get that same thing. So decreasing there. So now, since they say clearly indicate what facts and theorems you're using to come to your conclusion, I would say that our interval of increase is from here. And I would write it like this rather than one big interval, since this is an asymptote and can't technically be included in that interval. So this is our interval of increase, and our interval of decrease is going to be this. And then I would state that we use the first derivative test. So first derivative test, just to be thorough. Next, we want to find any relative maximum or minimum values, which we could do using this first derivative test or our second derivative test or the combination of the two. Looking at this, I see we're increasing and then we're decreasing, and it's at this point when x equals 0 that we hit that change. this goes on for infinity, and this goes on for negative infinity, so there are no relative minimums, but we do have a relative maximum at x equals 0. If I plug that back into my original function and figure out the y value, it's going to be 0, so it's at origin. And there we go. All we have to do now is determine our intervals of concavity. Give me one moment. I'm going to let my dog out of my room. Okay, now we know that we don't have any inflection points, which is okay, that's reflected in our interval. So now we're just going to check for what each interval is in terms of concavity. So I'm going to plug in these same values, but into my second derivative now. So it's going to be 32, so it's positive, times, this will never be negative, right, because this is squared and then plus. So it's going to be positive, positive. It's this where it might turn negative. So let's see, negative 3 squared is 9, 9 minus 4 is 5, 5 cubed is positive. So it's greater than 0, which means it is concave up. Just concave up there. Plug in that negative 1. That's going to be positive, positive over 1 minus 4 is negative 3. Negative 3 cubed is negative 27. So this is less than 0. So we're concave down. We're going to get the same thing there if I plug in that positive 1. So this is also concave down. And plugging in a positive 3, it's all positive. So it's concave up. They're just asking for what intervals it's concave up. So that's going to be negative infinity to negative 2, as well as 2 to infinity. Working our way down some more. Ooh, that's an ugly one. So now these are some integrals that they want us to evaluate. So the first one is an indefinite integral, but it is quite the mess. But I promise you, it's not as hard as it looks. Again, this one looks like it's probably going to need U-substitution. But again, I've said it before, and I will say it again. When it comes to U-substitution, sometimes you'll see it right away. Sometimes you'll need a little bit of trial and error. It's not always obvious what you need to substitute without doing a little bit of the math already, even if it's in your head, right? So U-substitution is typically a little bit of trial and error. There's not really any hard, fast rules for like how it should be done, to my knowledge anyway. But so I see that this part looks pretty similar to this. Like if I took, like if I took the derivative of like this bottom bit here, it would be this top, wouldn't it? Just without the 2x. Or ignoring the x squared, that is. The derivative of sine is cosine, the derivative of negative cosine is positive sine, because derivative of cosine is negative sine. So I'm going to try making my u value that whole bottom term. Now, of course, when taking the derivative, we have to use some chain rule, so it's derivative of the inside times the derivative of the outside. Oops. And derivative of the inside times the derivative of the outside. Oops. And now, from there, it looks like we can't use this at first, but we can just factor this out. So that's if I factor out those two x's, it's going to be 2x times cosine of x squared plus sine of x squared. And that's exactly what we have here, which means I can substitute this for u and this for du, turning our integral into du over u, or I could, if it's easier to understand, I could rewrite it like this. Looking at this, I know the integral of 1 over x, or 1 over u, is going to be the natural log of that thing, plus c. So now all I have to do is plug back in my u value, which is admittedly pretty long. So that's going to be the natural log, and keep it in the absolute value since it's an indefinite integral, right? So it's the absolute value of, the natural log of sine of x squared minus cosine of x squared plus c. Don't forget your plus c. The next one is a definite integral. This one also looks like it might need some U-substitution. So this is from 0 to pi over 3 of cosine 3x dx. I'm going to say that u equals 3x. That seems pretty easy. Du then is going to be 3. Obviously, we don't have a 3 to replace that with, but I can just divide that off. So it's going to be 1/3 du equals dx. So my integral is going to turn into this. I can put that 1/3 in front. So now it's just cosine of u du. I know that the integral of cosine is going to be sine, so it's going to be 1/3 times sine of u. I'm actually just going to plug back in that u value, so it's sine of 3x from on this interval. And now it's just a matter of plugging those in. I know 3 times pi over 3 is just pi. I know sine of pi is 0. And sine of 0 is also 0. So our answer is 1/3 times 0 minus 0, or 1/3 times 0, or just 0. Next up is an absolute value one, which tend to be, in my opinion, a little annoying. This one's a little bit more annoying than most absolute value problems we get. But yeah. So taking a look at this absolute value, we want to get an idea of where the center is, right? So I know that it's got something happening at x equals -1 and something happening at x equals 1, both of which are along these bounds. So I'm going to make just a little bit of a chart here to help get an idea of how I should split up my integrals. So I'm going to say I've got -2, -1, 0, 1, 2. If I plug in that -2, it's going to be 1 minus 4, which is 3, which I had to multiply by a negative, right, in order for that to work. So I'm just making a little note down here that I had to multiply by a -1, this whole thing, in order for this to make sense. Plugging in that -1, it's going to be 1 minus 1, which is 0. That doesn't matter if it's multiplied by a negative or not. Plugging in the 0, I get 1 minus 0, which is just 1. If I multiplied that by a negative and plugged in 0, it would be wrong. So that stays positive. I'm just making a note of that. Plugging in the 1, I get 0 again. Plugging in the 2, I get 3 again, and I had to multiply it by a negative. Which, annoying as this is, tells me I need to split this up into 3 separate integrals, right? So, let's see, I'm going to split it up from -2 to -1, where it doesn't matter here if I'm multiplying by a negative. So I say -2 up to -1, and for this integral, I'm going to multiply this whole thing by a negative so that my answer turns out positive. So it's going to be -1 plus x squared, or I could rewrite it like this. Then plus our second integral, which is going to be from -1 up to the next time, it doesn't matter. So -1 up to 1. And on this one, I'm not going to multiply it by a negative because it's going to turn out positive either way. So it's just going to be 1 minus x squared. And then our third integral is the rest of the way, right? So from right here, where I do have to multiply by a negative again, just like that. Sorry that that's crooked. I didn't really think out space. Now we just evaluate that, which is a little annoying. But of course, that integral is going to be 1/3 x cubed minus x, plus x minus 1/3 x cubed, plus that first one again, but on different bounds. And then we plug in all our values. So it's going to be -1/3 plus 1, minus, well, negative 2 cubed is negative 8, so minus 8 over 3, and then minus a negative, so that turns into a plus, but it's plus negative 2, so it's just minus 2. That's the first one. And we can combine like terms later. Or actually, this is really easy because that's plus 1 minus 2, so that's minus 1, and this is minus 1/3 minus 8/3, which is minus 9/3, or minus 3, so this is negative 4. Okay. Doing this next one, that's going to be a 1 minus a 1/3. I should write those a little closer together. 1 minus 1/3, and then minus negative 1, so it's plus another 1, because minus a negative. And then minus negative, so it's plus negative 1/3. Really hope I didn't just mess that up. But that looks something like that. So that's plus 1 1/3. And this next one, let's see, 2 cubed is 8. So I get 8/3 minus 2 minus 1/3 plus 1. So that is negative 1 plus 7/3, which 1 is 3/3, so that turns into 4/3, or 1 1/3. Now, this shouldn't be negative. Did I make a mistake? I definitely made a mistake, because none of these areas should be negative, so this shouldn't be negative. I feel like I probably just plugged things in wrong. I promise. I assure you this should be the right thing. Should multiply by that negative, blah, 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 blah. I'm gonna re-plug that in, so it's negative 1/3 plus 1 minus, oh, yep, plugging in the negative 2 gets me negative 8/3, but I am subtracting that, so that should be like that. And then minus, yeah, yep, that should be plus. Dang it, I knew that was too good to be true. So then that is negative 1 plus 7/3, which is just the same way as we did that, which is 1 1/3, which of course that's 3 1s and then 3 1/3, so that's just going to equal 4. And that is the correct answer. I remember that from checking my work earlier. All right. Now this next one's a little different than we're used to. So it says f of x equals x cubed, this integral from 1 to x cubed of e to the t squared dt. Okay, so we first want to compute f of 1. So I'm just going to plug in a 1 for x, which is going to be, so f of 1 is going to be 1 to 1 cubed, which is just 1 to 1. Da, da, da. And we could do that. I recognize this is from itself, though, which is, if we know anything, it's just going to be 0. But if you want to see why that's 0, of course, I'm going to have this integral, which is something, but then I'm going to plug in this bound, and then I'm going to subtract the bottom bound, right? So I'm just going to subtract it from itself, which gets us 0. So f of 1 equals 0. Now I want to know f prime of 1, so we have to take the derivative of this now, which uses that fundamental theorem of calculus. So because it's only this top bound there, that is, so it's going to be the derivative of this whole thing. Which using that fundamental theorem of calculus, I know the derivative is going to be just that. Which means that then if I plug in a 1 there, so it's f prime of 1, that's just going to be e to the 1 to the 6th, which is just e. Nope, I made a mistake. Backing up. Backing up here, taking that derivative, right, because this isn't just x, this is x cubed. Remember, we multiply by the derivative of that first, and then plug that into there. So it should be this. Now plugging in the 1, that's going to get me 3 times e, so it's going to be 3e. There we go, that's correct. Now I want to find the equation of the line that is tangent to the graph at 1, 0. So this is, of course, our slope at this x value. So, and since I know my x and y values, I can just use point slope form, which is really easy. So it's y minus 0, which is just y, equals the slope, which is 3e, times x minus that x value, which is 1. And boom, I can just leave it like that. Now, question 8, we luckily don't have to evaluate, we just have to set up the integrals. This one's really, really tough, so if I do a poor job of explaining it, that's why. Apologies in advance. Okay. Just checking that I'm still recording, because it has cut out on me in the past. So taking a look at this first one, it says, set up the area of the region bounded by the x-axis, f of x equals x to the 4th plus sine of x. Oh, so bounded by this function and the x-axis on the interval 0 to pi over 2. And we should include a brief explanation of why f of x is non-negative in the given interval. Looking at this, so this is continuous on this interval, right? We know that it's continuous, there are no discontinuities from 0 to pi over 2. And any value that we plug in on this interval is going to result in this being positive. Therefore, due to that, and considering like our intermediate value theorem and whatnot, since there's no negative values, since it's continuous and does not cross the x-axis on this interval, because it doesn't cross 0 on here, and it's positive. Whew, I'm doing a poor job of explaining this. Then the whole thing is non-negative. And I know that this doesn't cross the x-axis on this interval because the only time that this equals 0 on this interval is when x equals 0, and that is one of our endpoints. So like that doesn't change anything. Therefore, since that's non-negative, we can just do the integral. So the area is going to be the integral on those bounds. So it's going to be, oops. So, oh my goodness. Okay, so it's going to be from 0 to pi over 2. And it's just going to be that, because it's bounded by the x-axis and it is non-negative the whole time. So it's just that function. Okay. The next one is trickier. It is the area of the region bounded by two curves. So f of x equals sine of 2x, and g of x equals negative cosine of x on the interval 0 to pi. So of course we want to check for any intersection points, which is the difficult part with this one, and I really don't know how to explain how to find it. Generally speaking, you'd set these equal to each other and see when they're equal, because that's when they intersect. Because these are trig functions, that becomes significantly more complicated for most people. In this case though, so sine of 2x equals negative cosine of x on this interval only at when x equals pi over 2. And that makes sense because, of course, if x equals pi over 2, then negative cosine of x is 0, and 2 times pi over 2 is pi, so sine of pi is also 0. Then we just need to determine which one is on top and which one's on bottom on either side. So, because this is right smack dab in there. So I'm going to take a look at, on this interval and then on this interval and see which one is my top function, which one's my bottom function for each one, so that we can write out those integrals appropriately. So I'm just going to plug in a value for each of these. So let's say f of pi over 4, that's going to be sine of 2 times pi over 4, so that's sine of pi over 2, which is 1. G of pi over 4, however, is going to be, well, cosine of pi over 4 square root of 2 over 2. So it's going to be negative square root of 2 over 2, which is less than 1. So my f of x is my top there. My bottom is the g of x. Next up, we want something on this interval, and we'll just say 3 pi over 4. So f of 3 pi over 4, well, it's going to be 2 times 3 pi over 4, which is 6 pi over 4, or 3 pi over 2, which, if you'll remember, a unit circle is right here. So sine is -1. And then g of 3 pi over 4, that's going to be, we'll see a cosine there is going to be negative square root of 2 over 2. Since this is negative, that's going to be positive square root of 2 over 2, which is bigger than -1. So in this case, my top is g of x and my bottom is f of x. Now, in order to set up the integral for this area, it's just going to be 2 integrals. So it's going to be from 0 to pi over 2 of f of x minus g of x, because that's my top minus my bottom. So it's sine of 2x minus negative cosine of x, so it turns into plus. Then plus our second integral, which is from pi over 2 to pi, which is the opposite, right? So it's negative cosine of x minus sine of 2x, and both of these do actually turn out positive. Okay, now that is all the questions that were actually on this past final exam. But again, I did add just a few extras to go over just so we can get really thorough review. So number 9a says let f of x equal x squared plus 1 and g of x equals x plus 3. We want to find the area of the bounded region between these graphs. Okay, and oh, luckily we don't need to simplify. So that's nice. But we do need to evaluate it, I think, because they want a numerical answer. So again, we want to check for intersection points. And I'm going to subtract 1 and subtract x. So it's going to be x squared minus x equals, that cancels, that gets to be 2. X squared minus x, I'm actually going to subtract that, so x squared minus x minus 2 equals 0. Can I factor this? Yes, I think I can. So it's going to factor to x minus 2 times x plus 1. And feel free to FOIL that out to double check. So these, and so that equals 0. So these intersection points are when x equals 2 and x equals -1. Now, we need to figure out which one is on top, which one's on bottom. So say x equals -1 and x equals 2, right? And so let's pretend that we have, so it's gonna look something like that, I think, is probably how they intersect, is probably like that. So it's probably going to be like this. I am assuming that g of x is on top and f of x is on top, or sorry, on bottom, but we should double check that, of course. Wow, that's a really good sketch. Sorry, I'm just kind of impressed with that. So let's plug in a value between these, which we'll just plug in 0 for ease. So f of 0 is going to be 1, g of 0 is going to be 3, which confirms it. G of x is the top, f of x is the bottom. So that's going to be an integral from -1 to 2 of g of x minus f of x. So it's going to be x plus 3 minus x squared minus 1, which I can combine, and I'm going to put that in standard form. So -x squared plus x plus 2 dx. And now we evaluate. Oops. Or now we actually take the integral, rather. So undo those power rules. And then we've got to plug in those values. So it's going to be, let's see, 2 cubed is 8. So it's -8/3. 2 squared is 4. 4 halves is 2. It's 4. And then, so minus, okay, just so we don't lose anything. So it's going to be minus negative 1/3 times negative 1 cubed. So it's just going to be 1/3. Plus negative 1 squared is 1. So plus 1/2 minus 2. And of course distribute that negative. So that's negative 2 1/3 plus 6 minus 1/3 plus 1/2 is 5/6 minus negative 2. Okay, so I've got 8 minus 2 1/3, so I'll say that's 6 minus 1/3 minus 5/6. I know minus 1/3, that's going to give me 5 2/3, which is then 4/6. If I subtract 5/6, that's going to get me 4 5/6. So there is our answer. So A equals that. Next up it says the graph of the equation, this was a long one, 4x squared plus 16x plus 9y squared minus 18y equals 11 is an ellipse. Good. Identify the center and vertices of the ellipse and sketch the ellipse in the xy plane with appropriate labels. So first let's put this into a form of ellipses that we recognize, right? So remember our equation for an ellipse is x minus h squared over a squared plus y minus k squared over b squared equals 1. So I'm going to first, I see I've got an x squared and an x, which means that there's definitely some factoring I can do there. So let's put, we'll take out that 4, so it's 4x squared plus 4x, which I want to complete that square. So I know what would get me that would be x plus 2 squared, which if I complete that, it's going to be x squared plus 4x plus 4. Backing up, sorry. Gonna back up because I don't think it was wise of me to factor out that 4, actually. I always get a little thrown off when there's these extra when there's this extra coefficient in front, just because it's a little trickier to think about, or at least for me it is. Double check that we're recording. Good. Okay. Let's see. Well, okay, if I did factor out that would again be the x plus 4 squared, which is then 4 times x squared plus 4x plus 4, which would mean that we need an extra 16 in here. So that's going to be this. And so, of course, if this has brings us a 16 that we don't see in here, we're going to have to subtract that in order for this to stay equal. So now this should be the same thing, right? And I subtract that 16 to compensate for the added 16 right there. Now I'm gonna just move that 16 over there, actually. So just to make it a little easier to deal with. So that becomes a 27. And now I'm going to do the same factoring with my y. So I'm going to factor out the 9. So it's y squared minus 2y, which is not my favorite. So I would then complete that square. That's going to be 9 times y. Oh, dumb mistake. First of all, definitely wrote x plus 4 squared when that's 100% a 2. Whoops. That's a 2. Of course, that's okay to be negative because that just means that it is y minus 1 squared. Because if I FOIL that out, I'm going to get y squared minus 2y plus 1. Which means that I'm going to have an extra 9 that I need to subtract. So this is going to be 4x plus 2 squared plus 9 y squared minus 2, nope, sorry, y minus 1 squared, and then of course to counterbalance that 1 times 9, I'm going to subtract 9, which I can then add over there, equals 36. Now from here, it's pretty easily workable. Oops. Because from here, in order to get it into something like this, I just have to divide it all by 36, right, to make that equal to 1. So it's going to be 4 divided by 36 for that, which simplifies, what does that simplify to? 36 divided by 4 is 9. So it's going to be x plus 2 squared over 9 plus 9 divided by 36. It's going to be 1/4. So it's going to be y minus 1 squared over 4 equals 1. Which means that our vertices, so it's going to be h comma k, so that's negative 2 comma 1. So our vertices, nope, sorry, that's our center, not our vertices, because it's an ellipse. Sorry. So our center is at negative 2 comma 1. Our major axis is the x-axis with a radius of 3, right, because a squared, and this is a radius of 2, which means that our vertices on the major axis is going to be negative 2 plus or minus 3. So it's going to be, so vertices are going to be, let's see, negative 5 comma 1, 1 comma 1, and then we also have to do, because it looks like this, right? So those are those vertices from the center point, and then we have to add on this radius, so it's going to be 1 plus 2, so it's going to be negative 2 comma 3, and negative 2 comma negative 1. Okay. Now, so that's all our vertices, and like I said, the center is negative 2 comma 1. And now we just need to sketch it, and I can actually just figure not drawn to scale. So that's 0, 0, because that's, well, it's our x and y. That's 0, 0. Nope, because it's not centered at 0, 0. I'm a bright one. Sorry. So this is going to be negative 2 comma 1. Ah, screw it. I'll just draw a little coordinate plane because that's what's actually wanted here. So let's see. Center is at negative 2. So, and we've got vertex at negative 5. So that's negative 5. 2, 3, 4. 2. 5. 1, 2, 3, 4. Okay. And our highest thing goes 2, 3, 4. 1, 2, 3, 4. Okay. So our center is right here. One of our vertices is here. Another is here. Another is here. And another is here. So our ellipse is going to look, oof, that was ugly. Our ellipse is going to look something like that. That's our sketch. Okay. Sorry. Okay. On to number 10. So it says a substance grows exponentially. So we use that exponential growth and decay. So it's P of t equals the initial value times e to the power of our rate times t. And its weight doubles every 3 hours. Suppose it weighs 2 pounds at noon. After how many hours will it weigh 9 pounds? So we'll say that noon is when t equals 0, because we're talking hours after noon. So I know it weighs 2 pounds, which means that our P of t is going to be that initial value, we're going to say is 2 times e to the kt. I know it doubles every 3 hours. So 3 hours from now, it's going to be 4. Which, of course, that's just going to be this. Which now I can solve for that k value. So I'm going to use those properties. I'm going to say natural log of 2 equals 3k. K equals natural log of 2 divided by 3. Which means our function is now this. So now we want to know when it weigh 9 pounds. So it's going to be 9 equals 2e to the kt. And now we just solve for t. So we're going to divide that off. So it's going to be 9 halves equals all of this, which means I then take that natural log. So I'm going to get that. And now just divide both sides by that. So it's going to be t equals this. There we go. Then whatever number that is how many hours it will be. And it says do not try to simplify your answer, so I will leave it like that. So I'll say it is this many hours after noon. Okay, and then our very last question for this review is a pretty straightforward one. It's more physicsy. It says a car is moving initially at 44 feet per second. So we know that initial velocity is 44 feet per second. And it decelerates at a constant rate of 4 feet per second squared. So I know that the acceleration is a negative 4 feet per second squared. Determine how long it takes until the car stops. So it's going to be, our final velocity is going to be 0 feet per second because it's going to be stopped. Using this, now we just have to remember one of our equations. So our final velocity equals our initial velocity plus the acceleration times t. So let me just plug everything in. So 0 equals 44 minus 4t. Then, of course, I can just work with this. So that's 4t equals 44. So t equals 11 seconds. So it takes 11 seconds for the car to stop. And that's it. There we go. We've done. Oh, Lord. That was a lot of goodness. This was a long little exam for practice. Okay, I hope that all of this made sense, and I hope that this was helpful and that we all do well on our final exam, everybody. Whew, good luck.